Hello everyone, in today's video we'll take up a problem that appeared in IOQP 2021. The problem says we have a large hemispherical water tank of radius r that is filled with water initially up to a height of r by 2. The water starts dripping out through a small orifice of cross-sectional area A at its spherical bottom. The time taken to get the tank completely empty. So we have to find the time it takes to completely empty a hemispherical tank in which water is filled up to a height of h by 2. So give this problem a try guys and check out the solution. So this is how the situation is looking like. We have a small orifice at the bottom and the area of cross section of the orifice is very small if you compare it to the free surface of the fluid. Okay, so and the problem wants us to find the time to empty it, right? And in order to find out that time, we need to first figure out the rate at which volume is leaving the vessel. And how do we do that? We know that the volume flow rate of a fluid through any cross sectional area A, we can simply write it as A multiplied by the velocity of the fluid perpendicular to the plane of that area. Okay, here the cross section, this small cross sectional area is given to be A. So the volume flow rate of the fluid that is leaving the container is going to be the area A times the efflux velocity, that is basically the velocity at which fluid is leaving the container. Okay, so and in order to determine the efflux velocity, we can use Bernoulli's theorem. So let's just consider any point 1 on the free surface and let's consider a point 2 on the orifice. So if we consider any streamline between points 1 and 2, we can apply Bernoulli's theorem between points 1 and 2. So after applying Bernoulli's theorem, the pressure at end 1 and 2 are the same because it's exposed to the atmosphere. Now using equation of continuity, we can say that A1 V1 equals A2 V2. But guys, the thing is, as A1 is massive in comparison to A2, we can almost assume V1 to be 0 because the rate at which the height of this container will decrease is going to be very slow, that we can almost consider, because the rate at which the height of the water level falls down is going to be very slow, that we can almost consider it negligible. Okay, so we can basically neglect this term, and as you might imagine, this actually just turns out to be our typical efflux velocity that we get, that we know as Torricelli's law, right? So and this just becomes root 2gh, where h is the distance of the hole from the free surface of the water. So now as we have determined efflux velocity, we can write the volume flow rate dv by dt. Okay, so now we have to find the rate at which volume is changing in our container. We need to first know what is the volume of the fluid in the container, and for this we need to be knowing a result, and that is the volume of a spherical cap. Okay, if you didn't know it, so the spherical cap, which is a shape which takes a shape something like this as in our question, if you want the volume of this element over here, it is going to be 1 by 3 pi h squared times 3r minus h, where h is the height of the cap. Okay, so we are going to be using that. Okay, so now we have determined the volume of the spherical cap, or the volume of the fluid in the container. Okay, so with that we can find the rate of change of the volume. So I basically use a chain rule of differentiation here. I differentiated the entire expression with respect to h first, and then I differentiated h with respect to t. Okay, so now this is the rate of change of the volume. Now this would equal a multiplied by square root of 2g h. Okay, and why did I put a minus sign here? It's because the volume of the container is decreasing. Okay, so now as you can see, we have a differential equation in terms of h. Now we can solve it. Okay guys, so now the limits will be at time t equal to 0. The height of the water column is r by 2, and when it completely empties up, the time is t, and after completing the integral and solving for t, you'll get the time as this particular value. And this was option C. So that was it for this video guys. If you have any doubts, you can comment down below, and do like and subscribe if you enjoyed the video, and thanks for watching.